Alright, let's look at shear and bending moment diagrams. Just a quick note, this is one of my least favorite topics in mechanics. So let's take a quick look at it. These are going to be simple examples. So just to understand the basics, so express the shear and moment in the beam as a function of x, and then draw the shear and bending moment diagrams for this designated beam. So for step 1, look at the entire beam and determine your unknowns. So here, I don't know why I called this C and this R, I don't know. I was half asleep probably. So I draw in my unknown reactions at the wall. So Rx is going to be 0 because we have no other x force. Cy minus 9 kilonewtons, so Cy equals 9 kilonewtons. And then I want to solve for Mr. Mr plus 9 times 3 equals 0, so Mr equals negative 27 kilonewtons times meter. So I found my unknown reactions. Okay. From there, I want to section the beam at x. So x can be any distance along the beam. We're just calling it x, right? And once I section it there, I have this 9 kilonewtons. And then I draw in my internal loads. So I have N, V, and MC. From here on, what I want to do is I want to solve for V and I want to solve for M because obviously that's what we're looking for, shear force and bending moment. So for V, I have negative 9 minus V equals 0, so V equals negative 9 kilonewtons. For MC, I have MC plus 9 times some distance x equals 0, so MC equals negative 9x kilonewtons times meters. So as you can see, V for the entirety of the beam will remain negative 9 kilonewtons no matter where I cut it. V is not a function of x, it's just a constant. So if I cut it at 1 meter, my shear force, my internal shear force is going to be negative 9. If I cut it at 2.69 meters, it's going to be negative 9 kilonewtons, no matter what, because it is not a function of distance. It's just a constant. On the other hand, the moment is a function of x, so it's a function of distance. So if I cut it at a different point and I analyze the internal moment, it will be different every single time because it depends on the distance. So I plugged in random points, right? 0 meter, 1 meter, 2, and 3, and as you can see, for every point I get a different moment. And that is what I end up using to graph my bending moment. So, like I said, your shear is not a function of x, so from 0 to 3 meters, which is the length of your beam, it will be negative 9 kilonewtons for that entirety. On the other hand, MC, from 0 to 3 meters, it varies, so I basically just plotted 0, 0, 1, negative 9, 2, negative 18, and 3, negative 27, and you end up with this triangular area for your bending moment. So this is a pretty straightforward example, so let's do another one. This one was an in-class activity, but just to refresh. So the first thing is look at the entire beam and solve for your unknowns. We've done this since probably test 1, so this should be very simple. Your f of x, so ax equals 0. Your f of y, ay plus by equals 0. You don't know either of these yet, so you have to solve for b first. I pin my beam at point A and I do the sum of the moments. So b times 6 meters minus 30 kilonewtons per meter, so that gives me that b equals 5 kilonewtons. I plug it into this equation and ay equals negative 5 kilonewtons. So because ay is negative 5, it means that it should actually be pointing downward at 5 kilonewtons. So these are my knowns now. Okay. From there, we go to section the beam. So I want to section the beam at some distance x, where x can be any distance along this beam. From there on, I want to determine my internal resultant loads, so N, V, and M. I don't really care about N because it's 0 and because we're only looking for shear and moment. So for f of y, I have -5 minus v equals 0, so v equals -5 kilonewtons. For moment, I have mc plus 5 times x equals 0, so mc equals -5x. So v once again is a constant. It does not depend on the distance, so no matter where I cut the beam, my shear force will always be the same. But moment is a function of distance, so if I cut the beam at 0, my moment is 0. If I cut the beam at 6, my moment is -30. And -5x, that's linear, so I know that it's going to be a line starting at 0, ending at -30, and it's going to be it's going to have a slope of -5. So I didn't decide to plug in every single point, but you can if you want to. So for the entire distance of my beam from 0 to 6 meters, my shear force is always going to be -5. For the moment, I plugged in points, right, different points, and plot them on my graph, so you can see that the moment ends up looking like this triangular area. Now these are pretty simple examples just to understand the basics. I definitely recommend reviewing the second in-class example, which was very complex, and in that case your shear force was a function of x, so it's important that you understand those examples as well.